I'm Jesse Toth. This is joint work with Ricardo Cucella, and today I'd like to tell you about an implementation of session types that, as the title suggests, tries to use a minimum of fancy type class hackery. So suppose that you'd like to order a pizza, and so you make a phone call, and there might be an informal protocol that you follow to order that. But if you wanted to write a program to do that in a language, you might have to get the protocol a little bit more precise. And one thing that you're going to run into is most of these languages have channels that are parameterized over one type that you can send and receive over that channel. So if we need to talk about lists of toppings, sizes, prices, and so on, then we're going to need some sort of sum into which we can put all those things, which means that when we read something off the channel, we have to do a pattern match. And so if we've got the protocol wrong, our pattern match is probably going to fail. And when we write to the channel, we have to inject into the sum. And so, you know, if we screw up the protocol in various ways, things could go wrong. And one solution to this problem, I think a nice one, is session types. And the idea is that we're going to put a more precise protocol, a more precise type on our channel. So instead of just saying it's a channel over which we communicate this, sum, basically everything, we'll say we want a channel over which first we'll receive a list of toppings and then send a size back. Well, we'll talk about linear types in this paper, in this talk. The question mark and exclamation mark for receive and send are more like the CSP ones, not the linear logic ones. Then we'll send our list of toppings back, find out the price, send the address, and close the channel. So that's pretty much the idea. So I'm going to give you a brief history of session types, show you how we got here, show you what they look like and what they're supposed to mean, go through a very simple implementation, not the full implementation of the paper, demonstrate it, tell you how we argue about its correctness, and then finish up by telling you all the stuff this doesn't do and compare it to some other things. Session types were proposed as a way to put protocols on communication in the Pi-calculus by Simon Gay and Malcolm Hall. And since then, there have been a whole bunch of different calculi for session types. And when I look at these, they're neat, but there's something that bothers me about them. And if you could read this, you'd see that sending and receiving and other such things are all special forms in the syntax of the language. There are 2 rules for type checking receiving, 2 rules for type checking sending, and so on. And some people have had sort of the insight that what this is all about is preventing aliasing. If we were to alias some channel with some protocol on it, then we might accidentally run the same part of the protocol twice. And we have a good way to prevent aliasing, which is why don't we make send and receive and so on constants in our language with a linear type. In this case, send will consume the channel that says you can send an alpha, and what we get back is just a channel that lets us do some other stuff beta. And our ability to send an alpha should then be gone. And to me, this suggested a natural way to implement it in Haskell. So we made a library. And our library lets you use control.concurrent for your threads, not some other threads that we give you. It handles multiple communication channels at once. And it will infer the session types if you have 2 different threads talking to each other. And the other nice thing you get along with inference is pretty reasonable error messages. This is what you've seen of session types so far. You can have a type that says you can send something and then go on and do other things, or receive and do other things, and you'd be done. And we'd also like to add the ability to say, I'm going to choose between doing S1 and S2 dynamically. So that's S1 plus S2. S1 and S2 means that the correspondent on the other end of the channel is going to choose. I have to be prepared to do either. And those are easy to write in Haskell. There's also sort of repetition. Sorry? Repetition. We'll get to that at the end. I don't have time to go into it here. Another thing that we need to consider then is if you're speaking a particular protocol on a channel, then at the other end of the channel, they can't be speaking the same protocol. You'll get stuck immediately. So we do know that where there are ints, there are going to be ints. Where there are strings, there are going to be strings. But we need to flip all the sends and receives, and we need to flip the internal choice to an external choice. So what we have here is a duality relation between protocols. And it looks something like this: send and receive are dual, internal, external choice are dual. And in Haskell, of course, we can make that a class. And we'll say that it's bijective, which again helps with the inference. But if we get rid of that, it still works, just less well. And that's pretty easy to do in Haskell as well. So we can check duality. Now we need to figure out how we're going to do our dynamics. So underneath, I'm going to assume that we have these very sketchy, untyped channel things. And if you look at unsafe read uChan, you'll see there it says if you have one of these channels, you can read whatever you like off of it. So if you do that wrong, bad things could happen. Pretty much a segfault will happen. The other thing about these, just notice, is they're synchronous, which means if you have one thread trying to receive, it's going to block. Another thread trying to send, it's going to block until they can sync up and send the message. So we've got that. And let's see how we're going to do this. The last question is, what are the types we're going to actually give to our operations, such as send? We'd like it to have maybe a type like this, but unfortunately in Haskell we don't have those lollipop things directly, right? We don't have linear types, but we do have a technique for when we need to thread things linearly through our program. Monads. But the state we have here is not runtime state that we're threaded through, it's actually type checker state. So we'll use an index monad, which is not a monad. And about an hour ago, Ken mentioned the same thing called a parameterized monad. So we'll use that to keep track of our channel. And just for an idea of what that looks like, if you were to squint and ignore the first and second parameters to m, then that, and you had monad laws, then that looks just like a monad. But what we're adding is these two indices. And if we have a computation, we can think of the indices as being a precondition and a postcondition. And if you want to stick two of them together there, you'll see that the postcondition of the first argument defined has to match the precondition of the second argument. And so we can use that to keep track of the types flowing through there. And we'll just use a little bit of do notation that we implement with the preprocessor to make it easier to read. And to make it extremely simple here, instead of juggling multiple channels, we'll just have one channel that's implicit in the environment of your computation. And we'll maintain the session type of that channel as the index monad. So here we see our session computation type with the indices S and S prime computing in A. And what we can think of that as being a function that takes a channel indexed at S and returns a channel indexed at S prime and an unrestricted A, which we can get out of bind and do other stuff with. But we're not going to be able to alias these channels. And so then we can give send a type, and this is pretty much the same type we had before, which is that send says, given an A, you're currently in a state where you can send an A and then do some other stuff S. After the send, you have S left to do. And you can't get at the old A bang S anymore. We implement this session thing. It's essentially a composition of a reader monad for that implicit untyped channel and I/O. And so all send has to do is get its hands on that untyped channel and send the value you want to send over it. So if we get the types on send and receive and so on right, hopefully we can make this work. But if not, we're in trouble. And of course, session will be an index monad. So here are the types of all of our operations. We've seen send. Receive is pretty straightforward. If you have a protocol that says that you can receive an A, then you can receive an A. You can close it when you're done. If the protocol says you have a choice between S and R, then you can choose to go ahead and do S, or to go ahead and do R. And so, of course, on the other side, if you know how to get from S to some state U, and you know how to get from R to U, then you're able to get from S and R to U, in each case producing an A. And I'll show you the implementations of these just to emphasize that they're quite simple. Receive is just going to read off the channel. Close is a no-op. To select the left-hand side, we'll send true over that channel. And to select the right-hand side, we'll send false. So on the other side, for author, it has to read a Boolean off and then dispatch to S or R, depending on what Boolean it got over the channel. So that's the idea. The last thing that we need is a way to actually run these. So we define the idea of a rendezvous point, sort of a synchronization object for a particular protocol. And you can create these in the IO monad. And the idea then is that this is the sort of a port on which you can listen for connections and connect, and that parameter S makes sure that everyone's speaking the same protocol. So accept says if you have a session computation for some protocol S and a rendezvous point that agrees with that, then you can go ahead and run that computation. Or at least you can block until you have someone to talk to. So request then lets you synchronize on a rendezvous point where you have the dual protocol. So the idea is if you have one thread accepting and another requesting on the same rendezvous, and they have dual session types, then they'll be able to talk to each other, hopefully without any problems. For convenience, in our demo, we'll have this little function connect that just takes two session computations whose types are dual, runs one in another thread, runs one in the main thread, and returns its result. So let's take a look. So here we are in GHCI, and let's say we want a session computation where we'll read two values off of the channel, we'll call them A and B, and then we'll send their sum back over. And so if we ask what's the type of that, it inferred that we have a computation that, given a protocol that lets us receive two integers, send an integer, and then go on and do some other stuff, will be to the point where we can do the other stuff. And let's make another one. This receives a value and sends its negation back over. And now we can stick these together with offer. So now we've built something that provides an external choice to whether to do the adding service or the negating service, and then closes the channel. And of course, it will infer the type of that as well. Now we see that this is a server for some protocol where the client will have a choice between doing the addition protocol or the negation protocol, or at least something with that shape. Let's make another server. This one implements negation on the right. On the left, it doesn't do anything. So we'll see that it has a different type there. On the right, it's still receive an integer, send an integer, and close. But on the left, all you can do is close. So we have these two servers. And we can make a client that avails itself of only the negation service. So it starts out by selecting 2 on the right, sends its argument, receives some response back, and returns that. And if we look at the type of the client, we'll see it doesn't really even know what kinds of stuff it's dealing with, other than that the protocol that it's going to run on has to let it say something, which is the same type of its argument, and what it receives back has to match what it's returning. And you'll notice there's an R in there that appears in only one place, which means the client is going to be polymorphic over whatever the server offers on the left, because it doesn't take advantage of that. So we can connect the client to server 1. We'll send 3 over the channel, and it sends us -3 back. So our negation service is operational. And we can also connect the client to server 2. And so our little bit of protocol subtyping is working. Let's see some error messages. Suppose instead we try to use the client to send true to server 2. Now the client has no problem with sending 2. If you look at its type, it just says A there. But because of the duality relation in the type of server 2, we should get an error. And in fact, we get a type error that I think is pretty decent. It just says, look, I expected you to send me an integer, but you sent me a bool. Or maybe the other way around. It might be from the client's perspective. Now, suppose we try to connect a server that just wants to close the connection immediately to a client that wants to receive a value and then close. That's no good either. And again, we see that in our type error, that one side expected to receive something, but the other was all ready to close. So we won't allow that. And here's one more possibility. Both sides want to receive at once. And we'll try that. And again, we get what I think is a pretty decent type error, that pretty much it sees that one side is receiving. It really would like the other side to send. And you can see that right there in the first few lines. So you don't get pages of incomprehensible error messages. So that was our demo. Now that you've seen this working, you might wonder, well, but does it really work? Or is there some bug in there that's going to cause things to go wrong? And we formalized this with two calculi that we think reflect what we've done in Haskell very well. One of which we'll call the unsafe calculus has unsafe channels. It does not have a soundness theorem because you think you're sending something of one type and the other side thinks it's receiving a different type, and everything goes downhill from there. We have a second calculus, which we'll call the library calculus. That's what L is for. And it actually has all the session type channel operations with the same types that you saw in Haskell. And then we have a little compiler, or you might even just call it a library inliner, that takes terms in the library calculus and replaces the session typed operations with definitions using untyped channels that look just like the definitions in our Haskell library. And so we do that, and we have a theorem that says if you write a program using the library and it types using the types in the library, and then you replace all those operations with their definitions using the unsafe stuff, then it still will either diverge or find its way to a result. The result will have the right type. And there are more details about this in the paper. There's sort of a simulation on it as well. So, you can handle as well. Though I want to show you a really brief sketch of this. Normally, session types will have some sort of least fixed point operator to express protocols with loops in them. And that's fairly hard to do in Haskell. So instead, we used round indices. So we'll have rec of some body creates a binding, and then you can refer to the body from inside the body with a natural number. And of course, we need the duality instances for that. And the other thing that will happen then is as we unroll a recursive session type, we're going to end up having to store the various places that you can jump back to in an environment. So now we need operations such as send to not only maintain the current protocol, but to thread through some environment. And there are other operations involving unrolling and jumping back that I can't show you here, but that actually change the environment. The other thing that I said we do is handle multiple channels at once. So to do that, we simply replace the single session type that we're threading through with a stack of capabilities. Or sorry, not capabilities, session types. And I'm not supposed to say that. And so then all our operations, such as send, will just act on the session type on the top of the stack, leaving the rest alone, and we'll have some operations to commute the stack. And you might say, well, that's very nice. Not very nice. I don't want to use a stack. I want to get these things by name. And you can do that using something similar to HList. And it works, but it doesn't play very well with inference and doesn't produce very nice error messages. And of course, it's not going to work in other languages. So one of the chief merits of this approach, I think, is that it's simple enough that it's not only going to work in Haskell, though it is going to be nicer in Haskell. So we might ask, what's the difficult stuff? We need some way to express duality. We can translate that directly into ML and write duality proofs ourselves. We can also write duality proofs at the value level in a whole bunch of languages. And there's also a technique that will let us avoid writing the proofs that's in the paper. And we need some way to write the index monad, which involves being able to write bind and being able to give it a type. I can't tell you really precisely what you need to do this, but I can tell you where we've gotten it to work. So it doesn't rely on a lot. We're not the first people to try to implement session types in Haskell. There are two other implementations that I know of. A few years ago, Nubar and Timon wrote a paper in which they implement session types in Haskell. And theirs is a little bit different from ours in that they're concerned with dealing with, say, you have a POP3 server which someone else wrote, maybe you follow the protocol, you know, but you want to make sure that your client follows the protocol, so you write down the protocol and then it checks that it does. And more recently, there's an implementation that's very full-featured implementation of session types in Haskell, but it uses really heavy-duty type class package. So that's the difference between that and this one. And we can just run down some of the differences. Everyone supports branching, but only Sackman and Eisenbach let you write, say, a 5-way branch. We have to write it as several 2-way branches. Everyone supports recursion, but we don't let you access your where you want to jump back to by name. The other implementations do. You might wonder why I'm showing you this when, in whatever partial order I'm constructing, we're somewhere closer to the bottom. But, well, we'll see. So multiple channels, we handle it, but again, we use a numbering scheme, and they use names. And NNT haven't bothered with that yet. Type inference. It's kind of irrelevant if you're only writing one side of the communication. We do it, and we're able to do it because we've done things simply, and that leads to better error messages. And last thing is, we have, I think, a bit more of a soundness argument. Sackman and Eisenbach have Haskell soundness, but they may not have session type soundness. It's hard to tell. So finally, just a question. I've yet to see a satisfactory treatment of exceptions in a context with substructural types. So in our case, we'll allow channels to be affine. You can be ordering the pizza, and when you hear the price, you can say, never mind, sorry, and bail out of your conversation. But there's no way that you can say, never mind, sorry, or the user didn't get back to me with a list of toppings, and pick it up again later, because where would you pick it up? So a question I've been wondering is there a way to use some sort of transactions, or even to use session types to structure communication inside STM, and would that be useful? So, thank you.
Thank you, Jesse. Any questions?
Slide on the bottom,
So thank you, that was very nice. I really liked what you did. So I actually have 3 questions, but I'll just ask the first one first.
Okay.
So, so in your work you say that the client type has to exactly match up with the server type, which might be a little bit uncomfortable because the client has to be exactly aware of the protocol the server implements. The server might actually be upgraded and allow more things. The client needs to be aware of that because you need to say exactly which service you offer. So have you thought about that?
Well, so in the example I showed you, the client type actually only cared about one service that the server is offering, and it was polymorphic.
But it needs to know how many services there are.
That's true. And if we had sort of k-way choices instead of 2-way choices, or some way to label our choices, which Sackman and Eisenbach do, I believe, then you can make that work. But ours isn't going to let you add new services.
So how about some kind of subtyping? For example, if the server says you can either do A or B, and the client says, well, I want to do either B or A, so the ordering has to match. So
yeah, that we don't have that sort of thing. I could imagine that you could always design your server where you have a service on the left, and when you go to the right, you have sort of a list of services with an opening at the end. But the client is still going to have to know what order those services are going to be in.
So, like Wood, I really like this. I'd like to see something so elegant. Made nice use of these index monads. The first place I saw those was a paper by Robert Atkins. Is that where you got them from?
I actually found them on my own and then went looking for something about them, and I found Acti, and I found the stuff that Oleg had done. And yeah.
Any other questions? John?
I guess there is a risk using your library that you might create a rendezvous and then try to connect 3 things.
Yes. It's fine to connect 3 things to it, but one of those things is going to be waiting for a 4th thing. Typically in session types systems, you'll have some sort of theorem that says you can get stuck but not badly stuck. And so if you get stuck waiting for someone to talk to, that's not badly stuck. But once you've started a conversation, if you were to get stuck partway through, that would be badly stuck.
So you have a kind of runtime pairing.
Right. So yeah. So you can wait forever for the runtime pairing, but once you go, then you go.
Any other questions? I have a question.
Okay.
So is there any restriction on what types you're allowed to send over a challenge? Are you allowed to send a session type over a challenge?
We do have a way to do that, and it requires, so obviously the type of send we have requires you to supply the thing you'd like to send as an argument to it. So we need a special form of send and receive for saying, I'd like to use the top capability on the stack to send the second capability on the stack.
Okay. And I have another question. I like a lot of questions. So you used functional dependencies, and they had it was like a 2-way functional dependency. Have you considered using type functions? Because it's typically the kind of case where you want to kind of compute the dual from a given type.
Yeah, so I considered using that, and I think what happens then is that you can go in one direction, but I don't quite understand how to get it to work. So if you have 2 things that are going to be communicating, and they've left some holes in some of their types, they don't use part of that, then the functional dependencies will let you sort of fill in those holes both ways and unify it. And without them, then you'll just say, R would unify with whatever. And I'd like that to work in both directions. And I don't understand the type functions well enough to do that.
John, one last question.
Quick observation based on Kuhn's question. In ASN1 protocol specifications, then the extension problem was dealt with just by adding a ... alternative to sums. You could simply do that. You did it in an example. You simply mark extension points by offering something which at present is not essentially. Then you can extend the protocol.
That's like extensible records, right?
Yeah.
Yeah, and you can do that, but you're going to end up with a fairly unpleasant shape, I think, when you're done. But yes, you can
Haskell sort of let you do this extensible record thing
Almost.
nicely. We don't think it was almost nice.
Simon, one last question.
So one thing that often happens in these in protocols between clients and servers is that the client makes a request of the server sends back a sort of unique channel on which to talk, right? It could be typed. And then we want a different type of results. So you could each time make up a fresh channel. So you mean
yeah, so you could.
So it would be more like continuation passing style.
Yeah, you can do it in a sort of channel passing style, where
Yeah.
the type of your channel says that not only are you going to send an int, but you're going to send a channel that includes the rest of your computation. I think that makes recursion a little tricky to encode, but you can do it.
But it has something of the same thing, because you in effect are doing channel, sort of channel CPS style. You keep returning a new channel, right? So I was just wondering whether you explore what programs would look like in that style.
I've thought about it. I've tried to actually do the thing where I consider if you're trying to speak 2 different protocols, and so then you need to sort of be speaking the product of those 2 protocols, and that blows up. But there might be a way to do it that I haven't worked through yet.
Okay, let's thank Jesse and the other speakers.